Hello and welcome to video NL1, Newton's Laws. This video is a review of Newton's 3 laws of motion and goes with chapter 4 of your textbook. I know that you've already covered Newton's laws before, but it's always good to take a quick review of them before we get into using the laws to solve problems. And this will also give us a chance to take a look at how these laws look using calculus. Newton's first law only holds true for inertial reference frames, which means that the acceleration equals 0, or that you have a constant velocity. So you always want to assume that you are looking at reference frames fixed to the Earth. And Newton's law of inertia says that every body continues in its state of rest or uniform speed in a straight line unless acted on by a non-zero net force, or an outside force, as we would say. So as I said, number 1, assume reference frames are fixed to the Earth. Having your reference frame fixed to the Earth means that the acceleration is 0, because as far as we can tell, when Newton's laws are applying, we aren't moving anywhere. The Earth isn't moving. We can't tell that it's spinning around crazy, so we can make this assumption that we have an inertial reference frame. Also remember that when we are talking about an object moving, that the mass of an object is not the same thing as the weight of an object. And so you need to keep in mind that the mass is a measure of the inertia of a body. And keep in mind that inertia is the tendency of a body to maintain its state of motion. Okay, so mass is the measure of the inertia of a body, or you can also think about it as the quantity of matter present. Weight, on the other hand, is the force of gravity acting on a body. And so remember that weight, which we also say is the force of gravity, is the mass times gravity, 9.81 meters per second squared. And keep in mind, weight is measured in newtons since it is in fact a force. And of course, mass we typically measure in kilograms. So again, law of inertia, Newton's first law, every body continues in its state of rest or uniform speed in a straight line unless acted on by a non-zero net force. Newton's second law says that the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass, as we see here with the equation that A is equal to the net force over m, or sigma F over m. The direction of the acceleration is in the direction of the net force acting on it. Keep in mind that this too is only valid in inertial reference frames. This is why when you are driving, if you have things on the dashboard of your car when you're driving, they slip off when you're accelerating, because that is not an inertial reference frame. You are in an accelerating reference frame. The car is accelerating, so the objects are going to have a force on it. We can define a force with this law by saying that a force is an action capable of accelerating an object. That's a bit of a different definition than what we've had before, but it works well in this unit, however. In vector form, because we always have to look at vectors, and we always have to look at it in our 3 different dimensions, this law can be broken down into these 3 equations, which means that when we are looking at a situation in 2 and 3 dimensions, which we are going to be looking at, you have to keep in mind that you will need to be separating out your accelerations into their different velocity vectors, into their different directional vectors and unit vectors. It also allows us to define mass, because if we have the same net force acting on 2 different masses, m1 and m2, then according to Newton's second law, the ratio of these masses can be defined as the inverse ratio of their accelerations. m1 over m2 are 2 different masses being acted upon by the same net force. That ratio of masses will be the same as the ratio of the inverse ratio rather, of their accelerations. So this is a new definition for mass. We have a new definition for force. And also remember that it is the sum of the forces that is equal to ma, not every individual force. So when solving problems, draw all forces clearly in the proper directions, determine which forces or components of forces act in the same direction as the acceleration, and determine the net force, or do it in the opposite order, find all the components or the forces that are acting, find their net forces, and then from there you will be able to determine the direction of acceleration. All right, Newton's third law says whenever one object exerts a force on a second object, the second exerts an equal and opposite force on the first. So for example, we have this car that's driving down the road. The action force then is the tires push back on the road. The reaction is that the road pushes on the car. With our rocket here, the action is the fuel pushes out on the air, and the reaction is the air pushes the rocket forward. Our little guy doing his exercises, the action would be him pulling on the spring. The reaction is the spring pulling back on him. Now, depending on how strong he is and how strong this spring is, this action-reaction pair could go horribly wrong. If the spring is stronger than his ability to stand still, when the spring pulls back, it could move him. So even though the forces are the same magnitude, they are in opposite directions and they act on different objects, so therefore the result of their forces could be different. And here, the third one, finally, we have the action of the ball is, the person is dropping the ball off the Leaning Tower of Pisa. And so the action force is the earth is pulling down on the ball. The reaction force is that the ball is pulling up on the earth. However, it's the ball that moves, not the earth, because the earth is so much bigger that the size of the force that the ball is pulling on it with is not enough to make it move. But that exact same amount of force is enough to make the ball fall. So action-reaction pairs, number one thing to keep in mind here is that they act on different objects, so they don't cancel. Number two is the result of these forces can be different, even though they are the same size force. And the third thing to keep in mind here is that, similar to what we were talking about in the last video about relative velocities, naming these forces is very important. You need to keep clear which object the force is acting on. So for example, in this first one, the force on the road by the tires should be written as the force on the road by the tires, so FRT. Whereas the force on the tires from the road would be written as FTR. So the object comes first, and where it's coming from comes next. Lastly, even though we are talking about two different forces on two different objects, their sizes are the same. So we can also say that FRT is going to be equal to a negative FTR. So when we come to adding these vectors together, it is important to remember that they are just simply negatives of each other. Okay, the final thing about Newton's third law, and really about all of Newton's laws, is that we have a few different types of forces that act on objects. We have objects that can be acted upon by forces at a distance, like gravity. Gravity is not an object that's touching something, and you can have objects that are not in contact with each other and still be affected by gravity. However, we also have objects that are in contact with each other, and when they're in contact with each other, there's a couple of other forces we have to keep in mind. So let's finish up this video by talking about weight and normal force. Remember that weight is the force of gravity on an object, F of g, and that it's equal to mg, as we had said earlier. Also keep in mind that the direction of this force is always towards the center of the Earth, which is the negative y-axis. So we can also write F of g is equal to, or the weight is equal to a negative mg in the j direction. So we can write it in terms of the j unit vector. When two objects applying the forces are in contact with each other, the force between the two surfaces is called the contact force. Makes sense. However, the component of this force which is perpendicular to the surface has a special name, and that is the normal force. Take this box, for example. In each situation, there are different forces acting on it, but none are large enough to make it move. So this box is at rest in all three of these pictures. In this first picture, when the box is simply sitting on the ground, or on the table rather, the normal force is a contact force between the two, and it is perpendicular to the other force that acting on this box, mainly its weight. So if I were to write the sum of the forces equation here, there's no forces in the x or the z direction, so I'm only looking at the forces in the y direction. So the sum of the forces in the y direction for this first box are the normal force, because it's going up, we will say up is the positive direction, minus the weight. And it is not moving, so that has to be equal to 0. Which is another way of saying that in this particular situation, and in all situations like this, the normal force is going to be equal to the weight of the object. Now, in the second picture, we have someone pushing down on the box with a force of 40 newtons, and notice that the normal force has gotten larger because, again, this box is not moving. So the sum of the forces in the y direction, we are going to have the normal force, and it is going to have to counterbalance not just the weight, but also our 40 newtons, and this is still going to have to equal 0. Lastly, in this third picture, we have the person, rather than trying to push down on the box, they're now trying to pull it up a bit with the string. Again, they're not being successful yet. So our sum of our forces in the y direction are going to be our normal force, plus it's going to get the help of the 40 Newton force, and those two together are going to work against gravity. And because it's still not moving, it's still going to have a total net force of 0. The reason that I'm showing you this particular set of diagrams is because you have to make sure that when you are solving for Newton's laws and you are solving for acceleration or net forces, that number one, you look at components, and here we only had the y component, but number two, that you keep in mind that we have negatives and positives, and this normal force, this contact force, is dependent on what's going on in the situation. In the typical situations, normal force is equal to weight. However, if you have extra forces pushing down, then the normal force is going to get larger because it's going to be as if it had a greater weight. Or if you have forces pulling up, it's going to be as if the normal force, as if the weight decreased, and therefore your normal force is going to be less. So again, draw your diagrams, make sure that you are drawing your forces in relative scale to each other, even if it's not exact scale, and it will be easy to make these equations come out correct. That's all for the review of Newton's laws. So bye for now.